Welcome to this demonstration video for my UI/UC interview for CS. Purpose of this video is to demonstrate how I go about instantiating my teaching philosophy in the kind of informational presentations that we give our students, either synchronously or asynchronously in this increasingly remote age. To give a bit of context for this video before I dive into the actual simulation, note that this video will be building up to an active learning exercise at the end of the video that will tie into the students' homeworks and the assessments, and then will become the groundwork for the second video in this class. So today's class is split into two videos, sort of ramping up to an active learning activity. That's what comes after this video lecture. What came before is the previous material in this course on probability and statistics for computer scientists. The assumption here is that this is right at the smack beginning of the course, only the second lecture, or class day in this case, third video, I suppose, for this course, where we've already defined probabilities, outcomes, outcome spaces, experiments, and looked at how it exists in various concrete illustrations, like dice, cards, as well as more practical applications that aren't tied to gambling. But that was the problem for the previous lecture. In this lecture, they'll be coming in with that knowledge of how you measure up probability. In fact, you'll even get a little bit picture of that in that I start all of my lectures by tying it into their previous conceptual schema and the previous understandings to make sure that what I'm teaching them are not just scattered bits of info, but actually form a coherent framework for understanding and analysis. So with that preface out of the way, context that this is in a probability course for computer scientists, focusing on computer science applications, and that we're building up towards a active learning exercise. And so this lecture is giving them a skill for conditional probabilities and later Bayesian inference. I can go ahead and get into the talk. Welcome, students, to this third video lecture where we get to dive into how we can use probability to empower our computer science, our algorithms, and our networks and systems. In this lecture, we're actually already going to start hitting the road on practical algorithms. We'll see at the end of today's two-video sequence that we'll have the very engine of contemporary machine learning developments, and that you will become machine learning practitioners. So get excited for that. But first, we're going to get something even more fundamental, where we get to look at how uncertainties relate to each other. So with that little teaser out of the way, let's dive right on into it. As always, we're going to start nice and slow as you all settle into your seats, pull out your notebooks, close out of your email tabs. If this review is old hat to you, feel free to bump up the video to 2 times or 3 times speed. But I'll let you know when we start getting into new material and you need to really start leaning forwards, slow down the video, and start transcribing things into notes, because some of this stuff will be on the test. For those following along at home in the textbook, the first video will be covering chapter 7.2 of the Rosen textbook, and the second video will be covering chapter 7.3. So, what did we cover last time? Well, we started at the very core, the central problem of probability, which is that the world is uncertain. No one knows the future. We don't know what's coming out next. Even something as simple as a roll of the dice, just a simple plastic cube. When you roll it, you don't know whether it will come out a 1 or a 6. But we do know one thing. We know that it will come out somewhere between a 1 and a 6 at the very least. We know it's not going to roll a 7. It's not going to roll a 23. It's not going to roll a -2. The dice, at least, has bounded uncertainty. And with that trick, we've already done something huge, where we've taken our world of uncertainty and we've hemmed it in. We've fenced it in. We've drawn a tight outline around it. And so that was the tool that we equipped ourselves with last time. This idea of being able to draw out all the possible outcomes and draw a boundary around our uncertainty. And so we did this with sort of a triad of steps, our measurement triad, as we call it, where we first start by asking what are the space of possible outcomes. We write this as big omega. some people get fancy and they call it the universe. The universe of discourse, or the universe of possibilities. I'm just going to call it the universe because it sounds epic, but just know that it just means the possibilities, the set of possibilities. So for a pair of dice, this is going to be a 1, 2, 3, 4, 5, or 6 for one of the dice, and then the other one can also come out 1, 2, 3, 4, 5, or 6. When you put them together, you can have a 1 and a 1 to a 6 and a 6, everything in between. So you have 6 times 6 possible outcomes. This is great. We've already limited our uncertainty to just 36 possibilities. And now we can do something even stronger. Well, let's say I'm playing a game where when I roll an 8, I win some resource. I'm very interested in when the 2 dice add up to an 8. This is an event. It is a collection of outcomes. And we were able to draw it on our space now that we have this pretty picture. We're able to see that an 8 is going to be, well, a 6 plus a 2, 4 and a 4, a 3 and a 5. Those are going to be 5 possible squares that add up to an 8. And bada bing, bada boom, we've already gotten chances. We've already have something that lets us not predict the future exactly, but at least predict the odds of some future outcome, where there's going to be 5 out of 36 futures in the universe of discourse that correspond to me winning. I have a 5 out of 36 chance. And so this is great for fair dice. For fair dice, all the squares are equally likely. However, what if our roll is a little bit more complicated? What if someone's brought weighted dice to the table? These dice are more likely to roll 1 and 2, more likely to roll lower numbers. So 1 and 2 are more heavily weighted. They've got so much more mass on them. We're going to color them in darker to signify that. The lighter squares have lighter weighting on them. Well, never fear. I can still calculate the event of my outcome. I just need to, instead of measuring the size of blue as its area, I'm going to measure the size of blue, the amount of blue, as its weight. And so we're able to just add up all the weights. And so in this sense, probability continues to be just a measure. We went from measuring area to measuring weight. And this is a hard mathematical fact, where we always refer to probability as a probability measure. And we'll talk about these weightings as probability mass or probability density, if you want to get really physicsy with it, once we get to continuous random variables. And in general, the intuition for probability is that you want to be thinking about it as a measurement. So this is the 3 steps that let us measure probabilities. And so with this tool in hand, let's look at something a little bit strange, a little bit curious, that will let us say even more things about the uncertain outcomes in the future. Because for dice, rolling forward with this example, when you roll a 5, the probability of rolling another 5, well, it's exactly the same. You can roll 5s so many times in a row until you're blue in the face. Similarly, if you're playing roulette and it comes up red and red and red and red and red, it comes up red so many times, you say, surely it must come up black next time. I put my money on black. That's the gambler's fallacy, and the casino wins. They'll be laughing at you all day and night. However, that intuition, that is a fallacy for a lot of random experiments, as we called them last lecture, is actually spot on the money for a deck of cards. If you draw an ace of spades, the probability of drawing another ace of spades, say in blackjack, is 0. It's impossible to draw 2 ace of spades in a row, at least if you have just one deck of cards. And so you see something a bit curious, where the outcome of the first random experiment affects the outcome of the second experiment. And by observing one random outcome, we're now able to limit the uncertainty of the second random outcome. And so we're not stuck to just drawing boundaries around uncertainty. We can now start saying how uncertainties depend on each other, how they relate, like family members or friends. They depend on each other. And we can see this using our measurement tools. We can see that dice, flat weighting all the way across, but cards has this curious structure. We can't draw an ace of hearts twice, and so that square has not just less weight, it has no weight. It's completely whited out. And so this band in structure is going to be what creates dependence. So let's go from just this intuition to something mathematical that we can take to any problem, and it will let us know whether the outcome of one experiment tells us anything about future uncertainties that we have not yet observed. So this brings us to the new material for today. You might want to decrease my talking speed from 3 times video playback to something reasonable, like 2 times. Again, we'll be covering chapter 7.2 in this video, so feel free to follow along at home. And we're going to be building up to an exercise, so make sure that you're paying attention at least enough that you're able to use the skill. And I'll make sure to call out the formula that you need to have in your notes that you'll need to use on the tests. Very good. So let's go through our measurement triad for a deck of cards. On the side, I'll also be doing the measurement triad for dice. It's straightforward. We've done it before, but it's helpful to see how it contrasts with the deck of cards, to see the difference between dependence with the deck of cards and independence with the dice. So let's get right into it. Dice, there's 6 possibilities for each dice. You multiply 6 times 6, you get 36 outcomes. That's straightforward. Deck of cards. There's 52 cards in the deck, so surely it must be 52 times 52. But hold up. That band of sort of snake eyes or drawing the same card twice, it's impossible for a deck of cards. So you have to subtract off all of those squares. So it's going to be 52 times 52 minus 52. The size of the universe of discourse is 52 times 52 minus 52. So many 52s. Very good. So with this size of, well, universe of outcomes, I can now start measuring up the probabilities of the events I'm interested in. In this case, drawing an ace of spades. Well, the probability of drawing an ace of spades on my first card, those are all of the hands in that red column. And there's 51 possible hands in there. Would be 52 possible hands, except again, this diagonal, that one white square gets taken out. So there's only 51. And similarly, if I was interested in the probability of drawing an ace of spades as the second card in my hand, well, it's going to be the exact same calculation. There's 51 possible hands that have an ace of spades as the second card. Very good. So far, the deck of cards and the dice looking pretty similar. Their probability of event A and event B are equal. But we're going to get into something a little bit curious, something a little bit strange, because we're interested in when we've already observed the outcome of the first random experiment, where we've already observed that event A has happened. And therefore, our universe of possibilities collapses to just what's inside event A. And so that's what this mixture of the red event and the blue event are going to be. It's going to be this purple event of how likely it is to observe event B, given that we already know that event A has happened. And in this analysis, I'm going to go ahead and re-highlight this whited out square that happens to be at the intersection of red and blue. That's going to be very important. Keep your eye on that. So let's compute this probability using our measurement triad. I'd be tempted to say that it would be exactly the same. Probably rolling a 5 on the second dice should be the same whether or not the first dice was a 5. But for the deck of cards, we're going to see something a little bit different. So let's do this instead of jumping through intuitions. Let's go ahead and compute it mathematically, so we can get something solid and portable, transferable. All right. So note that this little clause here that we say we already know something, we've already observed that event A has happened, means that the universe of discourse collapses to just those hands of cards that happen to have an ace of spades as the first card. We're limiting the universe of outcomes. And that means that when we normally divide by the big omega, 52 times 52 minus 52, instead we're just going to limit the universe of outcomes to red, and so we're going to just divide by the size of red, which is going to be 52 minus 1. And this numerator has to change too, because no longer can we consider all possible hands that have an ace of spades as the second card. We're only interested in the ones that overlap with red, where event A happens and event B happens, where ace of spades is the first card and an ace of spades is the second card. You can already see where this is going to break bad, because that's impossible. The intersection between red and blue is just that one white square. Whereas for the dice, it's just a regular square. There's one outcome that is the intersection between blue and red, and so its numerator will be 1 out of 6. But for our deck of cards, honey, that's whited out. That's going to be 0 outcomes. Now here we have our sort of catastrophic change. What's different between a deck of cards and the dice does indeed have to do with that diagonal structure, and it has to do mathematically with getting a 0 when we go to measure up the weights of the intersection between red and blue, where they overlap. Because now the probability of event B is no longer the same after you've observed event A. It went from being this very much non-zero number to being literally 0. 0 chance of event B happening. So we say that these two card draws are dependent because this purple probability no longer equals its original blue probability. Whereas for the dice, 6 over 6 times 6 is 1 over 6. The 6's cancel. It stays exactly the same. Dice are independent. The probability stays the same no matter what you observe. Or at least we can say that event B is independent of event A. This purple probability that we've computed by limiting the universe of discourse to just what's inside red is so useful that I'm going to give it a special name. I'm going to call it the probability of event B conditioned on event A already having happened. Conditioned just like if-then-else statements are conditionals. We're saying, what's the probability of event A of event B if event A has already happened? So I'll read this as event B given that event A has happened. In fact, this purple probability is so useful, let's make sure that we can define it for things other than decks of cards and dice. Well, let's go over what we did. We just followed the rules of measurement, where we first limited our universe of discourse, the universe of possible outcomes, to just what's inside red. We defined our universe of discourse as just inside red, so then our denominator becomes just the size of the red column. And we limited the part of event B that we're interested in to just the part of event B that's also inside event A. The square has to be inside of event B and qualify for being inside of event A in order to get added to the measurement. So for dice, that was just 1. For cards, it was 0. We're going to add up those squares. And so it just becomes a simple ratio of the intersection of B and A over event A. And that same ratio is going to hold if we're doing unfair dice or unfair cards, where we now have weightings instead of just areas. Where we're still limiting ourselves to just event A, we're only looking at all the weight that's in event A, and we're limiting the weights of event B that we're interested in to just the ones that are also qualify as being inside of event A. Event B and event A. Add up all those ones. All right, so this is the important takeaway. If you get nothing else from today, get this ratio, this definition of conditional probability as limiting the universe of discourse to just what's inside of the red area, and then limiting the numerator to just the part of blue that's inside of that universe, that red area. So we're going to get the probability of EB intersected with EA divided by the probability of EA. This definition will serve us well for that first exercise. Go and do it and report back. It will set the context for the second video for our class today. Thank you for your attention.